Hello, Precalculus student. This video is for chapter 3.7, rational function. So this is the third section of our study. We finished section 1, which study foundation of function or basic function theory. And then in the second part, we study polynomial function, including quadratic function. And here we are coming into the third section, which we will study rational function, exponential, and log function. So three different types of function. So the first one we're going to study actually belongs to part of chapter 3, 3.7. So this function is related to polynomial. That's why it's in chapter 3, because the form of the function in terms of formula is a ratio of two polynomial, n of x over d of x. And of course, we want d of x to be actually a polynomial function, not a constant function. So there is actually an expression in the denominator. So that would be a rational function. So the main thing we want to talk about, the first thing is domain of the rational function. And then we'll talk about how the graph look like, how can you recognize it's a rational function, and later on we'll talk about what are the important features of the rational functions by looking at its formula. So now, because the function has a polynomial function in the denominator and a polynomial function in the numerator, so the domain of the function naturally will become the fact that we want to avoid any divide by zero in the denominator. So when we want to find domain of a rational function, just like what we have talked about in chapter 1 of function, is you do not allow the denominator equal to 0. So to find domain of a function that has numerator, denominator, the domain would be the denominator exclude the zeros of the denominator. So you would solve x plus 7 equal to 0, which is the denominator. You don't care about what it is in the numerator. And you will solve the zero. So in this case will be negative 7. But you want to, for the domain, you want to exclude it. Okay, this would be the number that is excluded from the domain. Exclude x equal to negative 7. So in a number line, you would draw a number line that say, I have negative 7 here, but I do not want it to be in the domain. All these number, I'm fine. So in interval notation, it will be from negative infinity to negative 7, and then union from negative 7 to infinity, but not including negative 7. So that is how you exclude negative 7. Second one, we have 5x squared over x squared minus 1. Again, we ignore what the numerator is. The numerator talks about what the x-intercept is, because y would be 0. If x, you can solve x equal to whatever. But we want when we want to find domain, we look at the denominator. So again, we solve the case when is the denominator equal to it's 1. When is the denominator equal to 0? So it would be x squared equal to 1. X is equal to plus and minus 1 when you do square root plus and minus. Okay, when you do square root plus and minus both sides. But these two numbers are being excluded because it would make the function y undefined. So if you draw the number line, that means you would have two open circle on negative 1 and 1. And all the other can be in the domain. So your domain would be negative infinity to negative 1, union negative 1 to 1, and then union 1 to infinity, right? So you're just looking at what number can be put in your denominator or in your function. So to avoid undefined. So I have h of x equal to x plus 4 over x squared plus 3x minus 4. If we are to factor this, you would notice that the top is x plus 4. The bottom would be, if you were to factor it, because later on when you solve your equation, you have to factor it anyway. So we usually would like to write the rational function, if possible, in factored form. So let's see. When you multiply two numbers, they are negative 4. When you add them, they are 3. So it'll be 4, 1, but negative 1. So the denominator can be factored as x plus 4, x minus 1. Then you may say, well, should we exclude negative 4? Because I could cancel it and it would still be okay, right? So we do not. When we do domain, we don't look at canceling. When we do later on, when we do something called a vertical asymptote, you see how we're going to talk about those. Those are the point where the graph would break into parts. We will exclude that, but for the time being, we don't. Okay, so for the time being of solving the domain, this is what is written out. If it shows up in a denominator, it cannot be. So if we solve the denominator equal to 0, solve x plus 4, x minus 1 equal to 0, we actually solve it right away and without canceling. So x would equal to negative 4, x is equal to 1. So we want to exclude this. Okay. So you would say, okay, negative 4 is being excluded, 1 is being excluded, all the others are included. Right? So the domain would be negative infinity to negative 4, union negative 4 to 1, union 1 to infinity. So that is the domain part. Okay, even if you have factor and you don't cancel it. So we are going to look at graph of a rational function and also formula of a rational function. And before we look at graph, so there's tons of them. So if you let you look at some of the graph. So this is one of them. You see that they have some special feature, such as the graph is not smooth. There are breakpoints. Sometimes there are holes in it. Sometimes, and you can also see that they don't go to infinity like a polynomial, although the numerator and denominator are polynomial, but some of them, or most of them, actually flatten out when they go to infinity. Two very representative graph would be 1 over x. So still remember the two-kit function, we have 1 over x. Do you remember how to graph it? You have two asymptote, one vertical, one horizontal, like that, right? We also had later on, we'll talk about 1 over x squared here. And do you still remember 1 over x squared, what the graph look like? The graph look like a breakpoint here. The graph go to infinity on both sides, right? And then it flatten out to 0 in the long run. So we would identify these features by some names. So one is called vertical asymptotes. So vertical asymptotes are vertical line where the graph approaches positive or negative infinity as x approaches from left and right. So in 1 over x, you'll see x equal to 0 is called a vertical asymptote because it breaks the graph into two parts. On the left side of it, the graph goes to negative infinity. On the right side, it goes to positive infinity. It shoot up without bound. So that particular line is called vertical asymptote. Sometimes it exists. The second one is called horizontal asymptote or slant asymptote. So some has horizontal asymptote, some has a slant asymptote. A horizontal asymptote is a horizontal line where the graph flatten or stabilize on it, y equal to b, when x approaches infinity or negative infinity. So this is actually primarily called the end behavior. We abbreviate as HA. The third thing is a point called points called removable discontinuity. Sometimes we call it a hole. Removable discontinuity is a single point where the graph is not defined, indicated by an open circle. So you can see that the graph breaks up. Like, so for example, it would be going up, up, up like this. Oh, and then there is a hole here. That's called removable discontinuity. These are studied intensively in calculus, so we need to know about them. So all in all, a rational function may have horizontal or slant asymptote, one or both. They might have other asymptotes also. It may have removable discontinuity. It's not necessarily have it, but it may have it. And then it may approach positive or negative infinity on the left and right side of vertical asymptotes. So, so if you have a vertical asymptote, you could have the graph go to positive on both sides. You can have the graph go to negative on both sides. You can have the graph go to one positive, one negative, or one negative, one positive on both sides. So there's different cases. Usually when we talk about, when you look at the formula, you know when this shows up and when this shows up. So the next things is we look at more details and of the graph. Okay. So if I have 1 over x, we can see that the line that breaks the graph up is x equal to 0. So we say vertical asymptote is x equal to 0. It is a vertical line. And then there is in the end behavior, when x approaches infinity, y approaches 0, right? This is getting closer and closer to 0. When x approaches negative infinity, y also approaches 0. So y equal to 0 is the line where the graph flattens into. So we call this kind of notation the arrow notation, and we have used them before in polynomial when we look at end behavior. So we'll do the same here. When x approaches infinity, f of x approaches 0. When x approaches positive infinity, f of x approaches 0. But we also use arrow notation to describe vertical asymptotes. So in the vertical asymptote, you see in our case, I'm going to redraw it here. So on the graph on the left-hand side, the graph actually on the left-hand side, when it is close to x equal to 0, very close to 0, but on the left-hand side, you can see that y itself actually shoot down, become negative infinity. And on the left-hand side, we use this notation, x approaches 0, negative. That means left side, left of 0, smaller than 0. When it is x approaches 0 plus, that means on the right side, right of 0. What happened to y? Y go to infinity. So we can describe the behavior. So this is not the end behavior, but the behavior of the graph near the vertical asymptote. It shoot down and then shoot up. Okay. Increase without bound or decrease without bound. That's what they say. And let's look at another two-kit function graph. Is the square reciprocal function, and we know that it behaves like this. Can you tell what the vertical asymptote is? The vertical asymptote is still y equal to 0, right? Oh no, x equal to 0. It's a vertical line, x equal to 0, x equal to 0 here. And then what about end behavior? Oh, let's describe it. Let's say if x approaches 0, negative on the left side, what happens to y? F of x, or this case is g of x, right? We call it g of x. G of x will approach infinity. And on the right side, 0 plus is also infinity because they are going in the same direction. Why is that? Because they are even factor. Even factor. The factor, not even factor. This factor has an even power. Even power, kind of like the multiplicity of even. Then they will go to the same positive or negative infinity at the same time. Do I have horizontal asymptote at the end behavior? Oh, both of them approach 0, right? When x approaches infinity, and when x approaches negative infinity, f of x approaches 0. So we use this arrow notation to describe them. And notice when the multiplicity of x minus a is even, the behavior of the function on the two sides are the same. Let's look at this graph. So we have this graph. Can we find what the vertical asymptote is? Clearly, the vertical asymptote is x equal to negative 2, right? And then the local behavior is when x approaches 2 negative, the graph shoot down, right? Y approaches negative infinity. When x approaches 2 plus, y approaches positive infinity. And then what is the horizontal asymptote? The horizontal asymptote is y equal to 0, so it flattens around 0. When x approaches infinity and also negative infinity, y approaches 0. So that's how we describe them. We use arrow notation.